right?
Yeah, absolutely, yeah. So
Yeah.
I guess the best thing to do then is to do what, like a 2-year project where you spend thousands of hours proving it.
Yeah, we could do. We could
do
get
that.
a university involved,
Yeah.
so that it wasn't just us saying it.
That would
Seeing
work.
what happened.
So let's do that.
Let's do that.
And let's start that back in 2019, and then we can present it in 2021 at this
Yeah.
conference.
And here we are.
Okay,
There you
that
go.
works. Okay. So that's what we've done. And when I say us, I mean us as a business associated with research institutions and people that are completely non-invested financially in this but are interested in the pursuit of science on this, which we'll come to in a moment. So I guess one of the key things to talk about when we talk about performance is understanding how performance degrades over time. So there's a big difference between a mechanical part and a electronic part. So the reason that right to repair is interesting around agricultural is because most of the aspects of an agricultural remanufacture will require replacement of parts.
Mm-hmm.
They wear. So in a car, for example, or a tractor, you have pistons, those pistons move, there's an element of friction. That friction leads to degradation, wear and tear, you need to replace that part. Not everything, but aspects of it. That doesn't happen with electrical equipment. The more you use a CPU, you don't have a set number of hours that your CPU can be used before it runs out. You do with some mechanical hard drives, but you don't really have that with memory, you don't have that with systems boards, you don't have that with a lot of the equipment that makes up ICT. So the worry that they'll wear out isn't actually
valid.
Yeah, I guess. Yeah, I mean it's something you'd consider, but it's not. It doesn't degrade the performance.
Yeah.
So I guess the best way to do that is to run a set of thousands of experiments that prove that.
Yeah, so
that's
it's
what
not just you saying it.
Yeah, exactly.
It's machines that are measuring it. And
15 years of experience telling you this isn't a thing across hundreds of people in multiple businesses saying it isn't a thing. But let's take that knowledge and experience out of it and let's scientifically prove it, right?
Mm-hmm.
So that's what we did. So we carried out like-for-like scenarios, and in this case it's on servers. So in this case we took a Generation 9 server, which is circa 2014, and we had it everything brand new versus everything refurbished, side-by-side test them. And when I say brand new, I mean like videotaping them coming out of the box, undoing the packaging, completely making sure that this is factory sealed from the manufacturer.
And that evidence logged with the university.
Absolutely, because it has to be repeatable methodology. It has to be. It can't just be like, oh, this was new. Trust me. It needs to be. It needs to be clear. And then you carry out the tests, and you do every single component new, every single component refurbished. What's the performance look like? What's the inefficiency look like? Then you do component level swap outs one at a time. You swap out the CPUs that were new and put in refurbished ones. Run the tests again across multiple temperatures, multiple tests, and then hundreds of hours later you kind of got a series of information around that. You then put the new CPUs back in, and then you replace with refurbished memory, and so on. So you've worked through line by line every single component in a server, and what that'll give you is a series of test results. And those test scenarios will tell you that there is no discernible difference between the refurbished and the original in packaging equipment. Nothing. Thousands of hours of tests will tell you they're identical. And the way those tests are run, you use something that everyone in the industry uses. So you use spec power, or use a cert by spec power. So cert is what creates the performance and energy metrics for servers. And it's what all your manufacturers, your HPs, your Dell, Cisco, it's what they put inside the box for Energy Star rating. So you use the same tool that they do to prove their performance, to prove their performance on refurbished and on new, like by like. And then you've got a test set that's comparable. Mm-hmm. Now, the way cert works is it carries out a series of tests called worklets, and they stress different parts of the architecture, so the CPU, the storage, the memory, and they have appropriate tests based on that. And what you have is then a weighted mean, and this is important because 65% of the performance and energy efficiency is down to CPU. So 2/3 of what we're looking at from a performance point of view comes from one component. So you should really look at that component quite closely.
Yeah, because it's a beast.
Because it's the most important piece, yeah. And the CPU, there's a law associated with the CPU called Moore's law, which means that every 2 years it will either halve in size or double in density, so double in performance theoretically for the same size chip. And that law is called Moore's law. That's been around, technically it's been something around since the 1800s apparently, but specifically in regards to CPU architecture, it's the sort of 70s. And work that we did alongside with the Uptime Institute disproved Moore's law from 2015 onwards in CPU architecture. So what we had this doubling of performance, and we had this increasing in energy efficiency, and that was true. That's been true for 35 years. And then around about 2015, what you saw is the incremental change in performance dropped off. So it went from it being double to it being 10, 13, 17% improved performance. But what we actually saw at the same time, due to the density of the cores on them now, the actual active idle power was becoming less efficient. So where the server spends the majority of its time, and I'm using the word server, it could easily be laptop, where it spends most of its time is at active idle. So it's on, but it's not doing a right lot. And that's become less energy efficient in the new architectures of the CPUs, whereas the actual top-end performance is become incrementally, not double, but 13%. So I guess the analogy that's really good for this is having two cars. So you've got a car that does 190 miles an hour currently, so it can drive 190 miles an hour, that's its top speed, and you spend most of its time at 30 to 90 or 30 to 70, I guess, depending on how you drive. 70, it's 70. And it's spending most of its time 30 to 70, and it's very efficient at running at 30 to 70 miles an hour, top speed 190. The new ones have come out, they've got a top speed of 200 miles an hour. So if you need to drive at 200 miles an hour, your previous generation can't.
Yeah.
So you need to buy that race car.
But in a real life scenario.
99% of the time, and 99% of the population are only going to use it for that 30 to 70 miles an hour. And at that, it's worse than the previous generation. So on a car analogy, you basically bought the wrong car to drive to the shops. Mm. That's what we're disproving here.
Yeah, and this chart looks at the analysis of CPU trends over time.
Yeah.
So what we did was we tested that in a real life situation.
That's right. And we tested that across hundreds and thousands of scenarios where that can then spin out. So to do that, we look at configuration. So understanding now that refurbished and new are identical, and understanding this trend in CPUs, which is the key driver of energy efficiency and performance, we need to look at configuration cross-generationally now. So in this case, we're looking at brand new generation, I should say, versus brand new or refurbished or previous past. Yeah. So it's like for like. So we've got base configurations, and what you've got is a base configuration of the previous generation being 13% less performant, less energy efficient than new. So new is now 13% better. Mm-hmm. But that's 13%. That isn't 100%. That isn't twice as good. That's 13%.
And it's going to cost you a lot more.
Like a lot more. If you can get the parts.
Yeah.
Like if you can get them, because that's a problem too.
And if you don't mind spending a ton of carbon making it.
Exactly right. Yeah. So we're looking just entirely on cost. On the carbon cost, it's high.
Yeah.
So what then we look at is, would changing the configuration of the previous generation allow it to perform the same as a new generation? Mm-hmm. And in this case, the slide I'm showing at the moment, that's the change of just a CPU. So a base CPU to a slightly better one, not a top end one, but a slightly better one. It's now completely removed the deficit it had with the new generation, and it's made it 2% better. So now a previous generation one, just changing the CPU and keeping everything else the same and identical to the new generation, is now better. Performance, energy efficiency. Okay, that's good.
Yeah.
So we take the CPU out, we just change just the RAM, because the difference is really small, it's 13%, so it's no longer massive improvements needed. And what we find is that now the previous generation is 17% better. So it's overcome its 13% deficit and become 17% better just from doubling the RAM.
And this is what I find really interesting, because when I spoke to people inside the sector a few years ago, they would say, you always have to replace. The sustainable option is always to replace servers with the latest version, because of the efficiencies when you plug it in.
Yeah, and that's
it will use a lot less energy, therefore a lot less carbon, so therefore it's your most sustainable option.
Yeah.
What they were relying on for that information was CPU changes.
That's right.
And what we're seeing here is that doubling the RAM is cheating those CPU changes.
Yeah. Between these generations, because it's worth saying that like the generation prior to the ones we're testing, so we're looking at 9 and 10 now, you could never get a Gen 8 to outperform the Gen 9, because the CPU architecture was a 2012 CPU versus what would be 2014 onwards, and the 2014 ones wouldn't fit in a previous generation socket. So what you're saying is that we've hit this sweet spot in time where this is now true, whereas it potentially has never been true before.
Yeah,
and in the future it might cease to be true.
Yeah, but
right
what
now,
we're also saying is that you need to, again, look at what you've got.
Yeah.
And design the best system with what you've got in front of you.
For how you want to use it right now. And that's exactly right. And that's, so we're looking on that the final configuration we're looking at is exactly that. So making a RAM and a CPU improvement has a increased incremental effect, which makes it 36% better. So we're talking tiny improvements on components. So we're not talking about top-end components here. This is significant cost savings, and you need more than a decent base spec to improve that. So that's what we've got to. How that plays out when you put that through specialist software and you put it across a data center estate, and which is in the slide now, this is a 4-year cost projection of running a data center with 366 older servers, and what you could do to optimize energy, carbon, cost on a refresh. And in this case, it would say go from 366 servers to 56 previous generation. Now, it'd probably still be 56 new ones, but we're talking we can go previous generation, and that would save 3 million kilowatts of energy, 1,000 tons of carbon, hundreds of thousands of pounds worth of cost, And all that it's saving is all waste right now. It's waste payments on energy, it's waste payments on equipment and on maintenance. And that's what we're trying to do. We're trying to figure out how does that play into your estate. And this is the same thing with laptops, right? You've got a state of laptops, use them 3 years, they're probably good for 7 years. Double the RAM, and it'll save you a whole procurement cycle or a whole lease cycle on laptops for a tiny cost and a massive environmental saving, which is cool. So the most important thing is this wasn't done just by us. This has been verified by the IEEE. So the IEEE is probably the world's leading authority when it comes to technology. These are independently assessed people who have nothing to do with the industry, but just scientists, and they check the methodologies, they check the results, they check the hypothesis. A lot of questions, a lot of paperwork, and in the end, the work we're talking about here just got published in the Transactional Sustainable Computing in December 2020, and they've actually put a link on here. So you can actually go download that paper. It's all fully open sourced, which I think's beneficial if you're interested.
Yeah.
And that includes all the assumptions, everything else. So what we're saying here has been scientifically proven. This isn't opinion. This isn't a white paper. This is now an area of fact.
It isn't because Astrid and Rich said so.
No, because you wouldn't want to trust me.
No, definitely not me.
Trust some people that are smarter than me. And what we're saying here is the most of the testing's done on servers because that's what we're specialists in. But this is the same thing for laptops. This is the same thing for desktops. This is the same thing for NUCs, for workstations, for anything that's in your IT estate. The principles are the same. Component level upgrades can significantly improve the life of your products and allow you greater deals of customization, flexibility, cost savings, environmental savings. And that's what we're trying to get to, right?